Hi, we're group number 3, and we're going to present the design and simulation of a centrifugal pump. The objective of this project was to design and simulate a pump that presents a geometry proposal that responds to the specifications given and determine the operating curve. In this project, we designed a turbo machine, a device in which energy is transferred either to or from a continuously flowing fluid by the dynamic action of one or more moving blade rows. In order to do this, we use reverse engineering based on the specifications of a centrifugal pump from Grundfos.
To create the structure of the model, Autodesk Inventor 2022 software was used, which facilitated obtaining the internal volume of the CAD design shown in the presentation. This design consists of components such as the housing, impeller, and diffuser. A key aspect of the model is that it includes a rotation region where the impeller is located. This table presents the main specifications of the design pump and those of the manufacturer, which we will be discussed in more detail in future slides. On the other hand, the pump planes are presented.
For the mesh generation, we considered surface remeasure, polyhedral mesh, thin mesh, and prism layer mesh. Prism layers were located in thin and wall regions in order to properly model the fluid wall interaction. These places are delicate because they are what determine if the design is going to be good or bad. The prism layer total thickness near the wall was 0.004 millimeters, and the previous configuration ensures a Y plus that's lower than 1, in our case 0.117. We can also see there's a lateral and upper view of the impeller, and we have the wall Y plus. We ran 3 meshes: the coarse, the base, and the fine. The only difference between the meshes is the number of cells and the base size. According to this, we also made a comparison by head and by efficiency. When we see the head mesh comparison, we should choose the base, taking into account that it has a lower MSE and a similarly low CPU time. Nonetheless, we should also consider first the efficiency mesh comparison. Now, knowing that the fine mesh is the second runner-up in order to be selected compared with the base mesh, we have to see the efficiency mesh comparison. According to this graph, the one we should choose is the fine, taking into account that the MSE is the lowest, and this is our priority, to minimize this error between the manufacturer efficiency and our efficiency. So, taking into account the head and efficiency mesh comparisons, the best mesh for our design is the fine one. And here we have some of the key sections of our fine mesh. We have the cutwater and the volute, and the impeller from different angles.
The physical specifications that were implemented in this simulation were single-phase condition, incompressible flow, steady state, and turbulent flow. The Reynolds number was calculated for water and oil following the equation shown in this presentation, taking into account that the rotational velocity is in units of radians per second. The values for both fluids suggest a turbulent regime. Based on the high Reynolds numbers, the K-epsilon turbulence model was chosen, with a K-epsilon two-layers model, and the selected treatment was the two-layer all-white plus wall treatment. This choice was made because it is known from the literature that this turbulence model provides better performance for the turbulent flow that includes strong curvatures and rotations. The two-layer approach allows for a more accurate modeling of the viscous layer, taking into account the interaction between the flow and the wall. To initiate the simulation, the geometry was divided in 4 parts: inlet and outlet section, rotation, and stationary zone. Boundary conditions were assigned to the first 2 parts: mass flow inlet for the inlet section and the pressure outlet in the outlet section. The initial conditions was set as the atmospheric pressure of Bogota, the absolute pressure in 0 pascals, and the velocity as 0 meters per second in all directions. The following equations were used to generate the simulation reports. The 5 simulations were carried out for water and 5 simulations for oil. In each one, the flow rate was varied. The values used can be observed on the screen, as well as the physical properties of each of the fluids.
The results for efficiency and total head are shown here. We can clearly see that the results for mineral oil were lower than those for water. This is because the oil's viscosity is roughly 30 times greater than water's, and higher viscosity results in higher losses, and therefore a lower efficiency and total head. The hydraulic and mechanical power curves follow the same trend. The results for mineral oil are lower due to its higher viscosity, and it is important to notice that in all of the curves, the results for both oil and water are similar to each other.
Here you can see that 3 of the 4 points of head are contained within the error zone of 13% that was calculated with the RMSE of the heads. And in the efficiency comparison, we can see that although all the data points are not contained in the error zone, we have a really, really low error of 7% that was also calculated with the RMSE of the efficiency. This means that our data is really similar to the manufacturer one.
Based on the literature, it can be determined that the Grundfos curve is characteristic of a centrifugal pump with a radial flow, while the design one have characteristics of a mixed flow pump. This can be explained due to the difference in the specific speed value. The design pump has a value of 22.15 and the Grundfos pump has a value of 18.43. The above values allows us to affirm that the two pumps have different designs in the geometry of the impeller, which results in the variation of the optimal conditions, as it can be seen in the table and in the image present. This could be expected because different parameters such as angle of attack or the inner diameter were assumed to design this pump, values that will be probably different in the Grundfos pump. What was explained above allows us to understand why there is a variation in the efficiency and total head curves with respect to the Grundfos ones. This slide shows the theoretical head and the efficiency curves for radial and mixed flow. Note that the manufacturer's figure corresponds to the theoretical radial flow curves, while the figures obtained from the pump that was designed follow the trend of the mixed flow curves. Therefore, the form of entry and exit of the flow in each one of the two pumps will be different.
In these scenes, it's necessary to ensure that the velocity is higher in the water relay scenes, regardless of the flow rate. This is because mineral oil, being the most viscous fluid, tends to resist flow and as a result moves more slowly in the impeller. This in turn leads to a lower velocity. An important point to know is that the velocity should be higher the closer the fluid is to impeller core and decreases as the fluid approaches the discharge nozzles as the volume area increases. In these final scenes, which refers to the bit, we can verify that in some of the impeller blades, the water does indeed reach a higher velocity than the oil.
It's important to note that there are some type of swirls in the discharge nozzle at the shutoff point for both water and mineral oil. This can be due to the boundary conditions that we use for the simulation, or also because the only fluid moving at the moment is air. Okay, here we can see that the velocity throughout the impeller is greater than the velocity throughout the volute and the discharge nozzle. We can also see that there are some points that are more colored than others. These are called backflows or turbulence. They are basically in the cutwater or between the blades and the volute. And finally, we can see the differences between water and mineral oil at both of their flow rates at the best efficiency point.
It can be seen that the pressure with mineral oil is higher. This because oil is more viscous than water. Higher viscosity fluids can resist flow more, requiring the pump to apply more force to move the fluid through the impeller and the pump system. This increased resistance can lead to a higher pressure. On the other hand, it is important to note that the pressure increase within the impeller of a centrifugal pump is a result of the conversion of mechanical energy provided by the rotating impeller into kinetic energy within the fluid. This kinetic energy is then transformed into pressure energy as the fluid decelerates and flows into the volute, delivering pressurized fluid to the pump discharge outlet. This is shown in the comparison between water and mineral oil as the flow rate is increased. The value of Y plus represents dimensional distance from the surface of a wall to the first mesh node in the boundary layer. It didn't change significantly with differing flow rates for the same flow and boundary conditions because of the relevant factors were held constant. We have constant values of Y plus at different flow rates for water and oil at the same boundary conditions because the same mesh resolution was maintained near the wall surface during all the simulations.
When it comes to total pressure, mineral oil compared to water usually generates higher pressure in an impeller due to its higher viscosity. It is important to keep in mind that at a flow rate of 0 cubic meters per hour, oil appears to have a lower pressure, though this happens precisely because of that lack of fluid. Oil has a higher viscosity, and this resistance to flow makes it harder for the impeller to rotate, which is why in every other flow rate, the ones with oil have a darker shade of red in their corners.
Also, it is important to talk about cavitation. Cavitation is the formation of vapor bubbles in regions of low pressure and high fluid velocity and can reduce the flow performance of the pump. It can be seen in this comparison between water and mineral oil as we increase the flow rate, that the higher the flow rate, the greater the cavitation will be. Also, that the lower the viscosity, the greater the cavitation will be because oil has a lower vapor pressure than water. This means that it is less likely to boil at a given pressure. It is important to note that the color parts suffer cavitation because the total pressure is lower than the vapor pressure, causing a change of phase of the fluid. This can affect the performance of the pump. Here, there are the streamlines of the simulations performed at our best efficiency point in both water and oil. When performing reverse engineering, several challenges were presented, mainly making use of assumptions for the design and the modeling. Reverse engineering relies on the ability of accurate information about the pump design, specification, and operating principles. Also, we would like to recommend improvements for the design. First, improving the geometry, for example, expanding the width of the fillet, changing the base size to obtain more number of cells, conduct experimental validations, and finally, change the Y plus when the viscosity of the fluid varies. Finally, we can conclude that with viscous fluids such as mineral oil, the pump performance decreases. Also, that the difference in specific speeds indicates that the Grunfos pump and the descent pump have different geometries. As a result, the Grunfos pump behaves as a radial flow pump, while the descent pump behaves as mixed flow pump. Also, we can conclude that cavitation occurs when the total pressure is lower than the vapor pressure, causing a change of phase of the fluid and can affect the performance of the pump. For future projects, there is an opportunity to perform modeling for non-Newtonian fluids, conduct simulation for more complex geometries, perform simulations also in unsteady state condition, simulate various pumps with different impeller shapes, and finally conduct simulation by varying atmospheric pressure to observe how this parameter affects pump performance.